for the SECP256k1 version of the elliptic curve algorithm, so that you can implement it in whatever programming language that you want to. A Python version right here uses the module tinyec. If you do like pip install tinyec, you can use this module. Okay, and what we have here is the same parameters that are over here we have in here. So the name of the curve, p is the modulo p for the public keys, and this is the largest private key, or actually this is a 0 position. I'll explain that in a minute. A here is 0, B is 7, so that it satisfies the equation y squared equals x cubed plus 7. I can show you what I got here is pycoin, a package called KU. It just lets you type in any private key and it'll give you all the information, public key, the x and y coordinates and all that. So if I type in the very first, the private key of 1 for Bitcoin, that is this position right here. Okay, this is the generator point. So ECDSA Wiki page explains a little better. Right here, this is how you calculate a public key. Multiply the private key by the generator point and you get your public key. And we will ECDSA module, will import everything. And that is the text file that I just showed you guys. And we say pubkey equals curve.g, so generator, times 1. And then we bring up the pubkey. You'll see this one here matches our x and y coordinates here. Okay, you can check this for yourself. The y coordinate, there's the y coordinate right there, and you know, you could do also something like pubkey.x or pubkey.y, and it'll give you just those values if you wanted to check them. That's just a quick way to reference where you're at on the number line. So the whole idea here is that you create a public key to receive Bitcoin, and you sign the transaction with your private key. Every single public key that's generated is generated from this original generator position, from this guy right here, the original G, which this is the original generator position for, and you can check it with your own public keys and your own private keys. If you take the curve.g in this module right here, use curve.g, and you multiply it by any private key, you will get your public key. And so we'll take this guy, it's just a key that I've played around with. So we'll set this guy to K1 for key. Okay, pub key times K1. Okay, this is now our public key that I just created from this private key K1. So if I bring up the KU module and I private key, it gives me the same position. Your private key is, your public key pair is not the X and Y. Your private key is what you multiply the generator by to get your public key. So the whole reason that you wouldn't be able to look at, say, this right here and say, well, why wouldn't I just be able to divide this side by the generator, right? Well, it's because you're multiplying the number 1 by your private key to get your public key. So if you were going to divide by the generator, you'd be dividing by 1. And anytime you divide a number by 1, the result is itself. What a modular form is, it's clock math. Okay? If you only have 12 hours on a clock, our private keys are our numbers here, and our public keys are our letters. Okay? To communicate over a secure channel, you would take your position and you would multiply it by your private key and you get your public key. So like if you just pick one, say I pick 11, we're going to call this Alice. We're going to put her on 11. Her public key is L. She can tell everybody in the world L. Everyone in the world knows how to get to L. But nobody knows that L's private key is 11. Okay? Nobody knows that. They can only reference this way. When you send coins to somebody, you're sending it to the public key's address. That address is a hash function applied to the public key. That's a whole nother video. But anyway, let's call this is Alice's key. Okay, and then we'll say if we have our original generator, we'll call him Bob. Okay, his private key is 1. We all know that, and we all know his public key is V. So if these two parties were going to communicate over a secure channel, they would do something called the Diffie-Hellman key exchange, where Alice would tell Bob her public key, and Bob would tell Alice his public key, and they would swap places and then raise that position that they're on to their own private key. Okay, so from this guy he would go 1, and from here she would go, her private key is 11, so she would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now they're both at K. They both end up at the same position. Okay, now this happens for all positions here. The entire, it just keeps going around and around and around and around. So if you were going to say if I picked private key 16 and I wanted to multiply that twice or something, I would go 16, add 16 to itself. So I would basically say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, that which is here. So in this case, 16 times 2 modulo 23 is 9. Okay, a modular form is the remainder after division. Okay, basically if you were going to have a number like 10.5, the 0.5 would be the modular remainder. Okay, you wouldn't get this in the result. You would only get a 5 because you went past the 0 position. So you're left over here. Okay, all modular arithmetic works this way. So that's actually what's going on. I mean, anytime in binary, all you have is addition. Subtraction is just addition of a negative number. Multiplication is just iterative addition. So it's addition over and over again. Division is just iterative subtraction. I want to set this pub key here. Pub key times K1. We're going to set that to key 1. Well, every key has a modular inverse, because every function is just a version of addition. Like I was saying, subtraction is just addition of a negative number. So the only way that you can actually subtract a number is by adding its modular inverse. If you have a modulus that is an even number, the half position does not have an inverse. It is its own inverse. So in this case, with the clock, 12, half of 12 is 6. The only way you can get back to 12 or 0 is by adding 6. It doesn't have an inverse. But if you have 13 on here, okay, you'd have an extra position. So you'd have like 1 and 12 would be inverses of each other. And then you would have 2 and 11 would be inverses of each other if you had 13 on here. So odd number of positions is the key to what's going on here with Bitcoin as well, because every key has to have a modular inverse. Otherwise, you would have a public key that would not be able to sign for itself, essentially, because of the way the signatures work. So if you wanted to get the modular inverse using multiplication, because what's going on here is modular multiplication, you're going to think of everything as a big number wheel with n, this number, as the 0 position. Okay, so n minus 1 is the very largest key, and I can show you that here. The key of 1, the x coordinates match, but the y coordinates differ, showing you that they're modular inverses of each other, because the private keys are inverted of each other minus n. So if you want to know if you have your private key and you want to know its modular inverse, you subtract it from n. So what I would do here is I would say I would say n minus k1. That would be its modular inverse. Okay? If I wanted to do that with multiplication, what I would do is I would say k1 times n minus 1, but I would do it modulo n. Okay? That's how you get the modular inverse. For multiplication, you multiply by n minus 1. For subtraction, you subtract the key from n to get the inverse for addition and subtraction. So your additive inverse would be here, your multiplicative inverse would be here of the key k1 that we have here. This is my sample key that I'm just playing with here. I just chose this key. And like I said, our key 1 now is our new public key. So we said pubkey, which is our original generator, times k1 times n minus 1 modulo n, we get the inverse. See, the x coordinates match, y coordinates differ. You know now that the public key is a multiple of 1, and if you multiply a number by 1, it is itself, and if you divide a number by 1, it is also itself. So the only way that you can really divide anything on this right here is to break down the number n, which is the 0 position, because you're dividing by 0. Because everything is a modulo n, everything is a remainder after division. So the 0 in this position, you're dividing by 0 with every single function, and you're getting the remainder after 0, after dividing by 0 as a result. Like I said, if we take k1 and we multiply it by 2 modulo n, it equals that number. Okay, and now let's say we have our we're going to take that and we're going to multiply our public key, our original generator, by that. Okay, so pub key times that number is that, right? So what if we take our k1 times, our key 1, which is our public key, and we say key 1 times 2. We now get the same thing as if we multiplied it by the same number. See, so all you're doing is multiplying modulo n with every function. So if you really think about this, if you have a calculator and you wanted to divide by some number. If you wanted to divide by 2, but you cannot use division, how would you do it? You could use multiplication using a decimal, right? Oh, your 0.5, right? 0.5 in this case, what we would have here is we have n. N is 0, okay? So if we have n, we take and we divide using floor in Python by 2, n divided by 2. It's the same thing as if you were to, what it does is if it's a odd number, it subtracts 1, then divides that number by 2. As you can see, it gives you the same thing. What you would need to do is get the inverse of this number, which technically is n plus 1 floor divided by 2, or n minus n floor 2, which is subtracted, n subtracted from this number is its inverse. This here, this number, this is 0.5 in Bitcoin, okay? This is 0.5 right here. So if we any key you multiply by this, you can remultiply the result by 2 and it will give you the place you started at. Okay, so I'm gonna prove that by just labeling this half, saying n floor 2, n minus. Okay, and now we're gonna show you by saying key 1, which is that guy, our original public key, times k1, right? That's our private key for that position. Imagine we don't know that. So we'll take key 1, we'll multiply that by half, our half that we just defined, okay? Now we get our half of our position. Now we can go check this by saying k1 times half modulo n is that number, right? Take that guy and we're going to multiply it by 2 times 2 mod n. I forgot another parentheses. There we go. And we're back at the place we started. Just like if you take our key 1 times half equals that guy, and you multiply it by 2, you don't have to do mod n with pub keys. It does it for you. That's the thing here. But as you can see, we're back at our starting position. So whatever this number is, we know now it's this because we knew our private key. We know that we can find its half position, which is this. Now, one thing you'll notice here, this number is not half of this number. Because if we took our k1 and we divided it by 2, that's the same number, right? Well, the difference here is k1 is, if we did the binary of k1, it's not a 256-bit number, okay? I can show you that by saying like a equals big A, I don't want to mess up that binary, and then we'll tell you the length of that big A, 254. This is a 254-bit number. It's not a secure private key. Its inverse, its modular inverse, is a 256-bit number. So I think we did not do that. So we're going to say K2 equals, equals K1 times n minus 1 modulo n. K2, that's our modular inverse, right? So if we take our pubkey times K2, that is the inverse to key 1. So we're going to set that to key 2. let's just go up. We'll say key 2, damn it, equals that. Right? So now key 1 and key 2, we know are inverses of each other, and key 2 is our K2, which this is a 256-bit number, and I can show you that with the binary of K2. Copy this, and we'll say big B equals that string, the length of big B, 256 bits. As long as you have a 256-bit number, everything on that side of n over 2 is a secure key. Everything above 2 to the 255 is a secure key, and anything below n minus 1 is a secure key. So you have this entire half of the circle that's all 256-bit keys, except for a little tiny section at the bottom that's 255-bit keys. And then you have the same thing on the other side, but you have 255-bit keys in the little bitty section on the other side of the half, and the rest goes down to 1 bit. That's basically kind of like if you imagine it as a number circle from 1 all the way around to n minus 1. That would be the layout that you're going with bits here. Like all of your modular inverses, if you have a 256-bit key, its modular inverse is not going to be a 256-bit key. It is going to be 255 bits or less. I can prove that we're dividing by 2 here with our original generator, and if we multiply that guy by half, right, that's n plus 1 over 2. Okay, that's the 0.5. But if we also multiply it by half minus 1, remember we have half, and then half minus 1 is the same thing as n floor divided by 2. Okay, so this is the half position. Look how small this x coordinate is. So far, this is the smallest x coordinate I've seen. And you can notice here, this is where the number goes from 68 to 69, and if you change this guy to pubkey times half plus 1, that would be ending in a 70, right? Oh, well, I gotta put the parentheses around that because it doesn't know how to add 1 to an x and y coordinate. There we go. You can only add to the scalar and then multiply the public key by the scalar. So, okay. There's the plus 1. Now, if I did that half minus 2, it would be that inverse, see? X coordinates, same. Y coordinates are inverses. In order to divide by a number, you're going to use the division of n in the inverse form. So if you wanted to divide by, because I mean we just did that, we found the number times 2 that equals our original starting position, and we know that the generator is the 1 position. So if you can get back to the original generator from any public key using the key minus 1, you've basically figured out how to reconstruct a private key. We divided n by 4. We get that number, right? But if we wanted to divide using multiplication, we would need the 0.25 in the less than 1 state. Basically, it's the same way that we said n minus n floor divided by 2. So we would say n minus n floor divided by 4. Okay, it's that number. So now if we took our t1 and we multiplied it by this scalar integer, we get that public key. Now I can show you with k1 times the same, it's my okay, so this number right here, let's just set that equal to the letter C, so I can show you that C times 4 mod n equals our original private key. because we just divided by 4 using this scalar right here, which is it's n minus n floor divided by 4. Okay, so if you want to divide by 4, that's how you do it. And you can keep going. You can divide by 8, you can divide by 16, you can divide by 32, 64, and you can't divide by 128 without adding 66. I don't know why. I haven't figured that out yet. But stay tuned. Maybe we will one day figure something like that out. Just know that even if you are looking to maybe solve the discrete log problem, which is what the name solving this problem is, if you were to find the private key from the public key, you're not breaking the security behind Bitcoin, because the security behind Bitcoin is based on SHA-256 algorithm. And if you take one of these public keys, you have to hash it. As you see here, you have a 160, hash 160. What they do is they're taking this x and y coordinate and they're hashing it, double hashing it with SHA-256, then using RIPE-MD 160 to come up with this number, and then using the base 50, or yeah, this number here, this is the hex representation of it, and then the base 58 encoding of that give you your address. Okay, I mean, if you had somebody's public key and you found their private key, they just wouldn't want to reuse that address, would be the whole idea. I mean, you already lose privacy by reusing addresses. I never reuse it anyway, because the core wallet tells you you can spend your change to a new secure wallet, and that's what I recommend doing every time, because if you sign a transaction, you're releasing your public key, and if somebody can figure out how to divide enough times and stumble on the collision of your key, they might be able to find it. If you've signed enough transactions, it might be possible to reconstruct your public key from a private key. So the whole idea here is to not allow that, and don't reuse addresses. You won't give yourself away.